Welcome to our presentation on instrumental variables regression, a cornerstone of modern economics. We will explore the theory, diagnostics, and practical implementation using Stata's powerful ivregress command. Think of IV as a way to find the clean part of a variable that is otherwise contaminated by hidden factors. Let us begin by understanding why we need this method in the first place. The OLS, or ordinary least squares, estimator relies on a critical assumption that regressors are uncorrelated with the error term. When this assumption is violated, we fall into the endogeneity trap, leading to biased and inconsistent estimates. Look at the diagram on the left. We have an unobserved error, U, which influences both our endogenous regressor, x1, and our outcome, y. A classic real-world example is the returns to education. If we try to estimate the effect of schooling on wages, unobserved innate ability acts as that hidden variable U, affecting both how much education someone gets and how much they earn. Because OLS can't see ability, it mistakenly attributes its effect to education, resulting in an overestimate of the true returns. To escape this trap, we use an instrument, Z, which affects x1 but is cut off from the unobserved error U, as indicated by the scissors. This ensures that the variation in x1 we analyze is clean and independent of the bias. This decision matrix serves as a roadmap for choosing the most appropriate estimator when dealing with potential endogeneity. The process begins with a Houseman test to determine if the regressor is truly endogenous. If not, we stop and use OLS because it is more efficient with smaller standard errors. If endogeneity is present and valid instruments are available, we move to check the identification status. In a just-identified model, where L equals K, two-stage least squares is the standard choice. However, in an over-identified model, where L is greater than K, the choice depends on the error structure and instrument strength. We use 2 SLS for homoskedastic errors, but switch to the Generalized Method of Moments, or GMM, to gain efficiency if heteroskedasticity is present. If we are faced with weak instruments, limited information maximum likelihood, or LIML, is typically the more robust option. Always keep in mind the crucial trade-off noted at the bottom. Because IV estimators are less efficient than OLS, they should only be employed when endogeneity is proven. Stata provides a unified command, ivregress, to handle different IV estimators. Let's break down when to use which tool. First, 2SLS is your standard baseline. It is robust and intuitive, but be careful, it can become biased if your instruments are weak. If you suspect heteroskedasticity or non-constant variance, GMM is the more efficient choice. However, its performance can drop in small samples. For those small sample sizes or when dealing with weak instruments, LIML is a great alternative because it has less finite sample bias, though it often results in higher variance. Pro tip: if you're dealing with complex cluster-robust inference, don't overlook the user-written command ivreg2. It is a powerful tool often used in high-level research for more flexible diagnostics. Two-stage least squares acts as a data purification system. In stage 1, we use instruments as a filter to extract only the clean exogenous variation from our endogenous variable x, resulting in the predicted x hat. In stage 2, we use this purified variation to estimate the true relationship with our outcome y. The mathematical heart of this process is the estimator formula shown below, where the projection matrix P sub z isolates the variation belonging to our instruments. For this filter to be effective, however, our instruments must satisfy 2 critical criteria: relevance and exogeneity. For an instrumental variable to be valid, it must rest on 2 fundamental pillars. The first pillar is instrument relevance, represented by the chain link icon. This means the instrument Z must be correlated with the endogenous regressor X. Statistically, we check this using the first stage F statistic, where a value greater than 10 is the standard stock Yogo rule of thumb. The second pillar is instrument exogeneity, shown with the scissors icon. This requires that the instrument Z is uncorrelated with the error term U, essentially cutting off any direct path to the outcome. While relevance is easy to check, exogeneity is untestable in just identified models. We can only test it formally using over-identification tests, like the Hansen-J or Sargan tests, if we have more instruments than endogenous variables. The ivregress syntax in Stata is highly structured to ensure all components of an instrumental variable's model are clearly defined. You begin by specifying the estimator, typically 2SLS, LIML, or GMM, followed by the dependent variable and any exogenous control variables. The most critical part is enclosed in parentheses, the endogenous variable and its instruments separated by an equal sign. This is the pivotal definition that addresses the endogeneity trap. Let's look at the concrete example at the bottom. The command ivregress 2SLS wage, age, region, parentheses, education equals proximity estimates the impact of education on wages. Here, education is instrumented with proximity to account for potential bias, while age and region serve as standard controls. This single line of code manages the entire two-stage process efficiently. This slide outlines the workflow for preparing your data and selecting the appropriate tools for IV regression in Stata. We begin with a data prep checklist. It is standard practice to start with describe and summarize to identify missing values. Often, economic variables require log transformation, for instance, creating ln wage for log linear models. If you are accounting for time series correlation via hack errors, remember that TS set is mandatory. Next, let's look at crucial command options. VCE robust is vital for ensuring your standard errors are robust to heteroskedasticity. The first option is highly recommended as it outputs the first stage regression, which is your primary window into instrument relevance. For smaller datasets, the small option reports T and F statistics instead of Z and chi-squared. Finally, the SStat suite provides the necessary post-estimation diagnostics. Use SStat first stage for weak instrument tests, SStat override to check the validity of your instruments in over-identified models, and SStat endogenous to statistically confirm whether an instrumental variables approach was required over OLS. In this practice step, we're estimating the effect of housing value on rent, instrumenting it with family income and region. We use the ivregress 2LSS command in Stata, including the first option to see the first stage results. Looking at the regression output, the coefficient for housing value is negative 504.0671, with a p-value of 0.000, which is highly significant. However, a negative coefficient here is quite counterintuitive. This unexpected result highlights why we cannot take the initial output at face value in IV regression. We must move on to diagnostic tests to check the relevance and validity of our instruments. For instance, we'll need to verify if family income and region are strong enough instruments and if they satisfy the exclusion restriction. After running our regression, the first diagnostic hurdle is relevance. Are our instruments actually correlated with our endogenous variable? We use the SStat first stage command to find out. The key metric is the F statistic, and the rule of thumb is simple. We want it to be greater than 10. In our output, highlighted in the circle, the F statistic is 13.29. Since this is safely above 10, our instruments are considered strong, and we can move forward. If it were below 10, we'd have a weak instrument problem, risking a bias toward OLS results, and we need to consider alternative estimators like LIML or search for more powerful instruments. The second diagnostic check focuses on instrument validity through the over-identification test. This test evaluates the exclusion restriction, which is only possible when the model is over-identified. We use the Stata command estat override to generate these results. The null hypothesis, or H0, assumes that the instruments are valid and uncorrelated with the error term. Here, the Sargan test shows a p-value of 0.0103, while the Bassman test is even lower at 0.0050.
Since these values are below the 0.05 threshold, we reject the null hypothesis. This leads to a troubling conclusion. There is a problem with the instruments. At least one of them is likely endogenous, meaning our current results are not reliable. Our final diagnostic check is the Hausman test, executed via the stat endogenous command. This test answers the fundamental question: was an instrumental variable approach even necessary in the first place? The null hypothesis here is that your variables are exogenous, meaning OLS would be consistent and actually more efficient. In our results, both the Durbin and Wu-Hausman tests produce extremely low p-values, 0.0003 and 0.0002, respectively. Because these values are significantly less than 0.05, we decisively reject the null hypothesis. This confirms that endogeneity is indeed present in our model. The practical conclusion is clear. OLS is biased and inconsistent for this data, and our decision to use an IV estimator was the right one. In this final extension, we address the issue of heteroskedasticity. When the variance of your errors is not constant, 2SLS is no longer the most efficient estimator. Instead, we turn to GMM, the Generalized Method of Moments, which optimizes the weighting matrix to handle this non-constant variance. Note the shift in diagnostics. Whereas 2SLS uses the Sargan test under the assumption of homoskedasticity, GMM utilizes the Hansen-J statistic. The Stata syntax reflects this change by using the GMM estimator and the W-matrix robust option. Just like our previous tests, we are looking for a p-value greater than 0.05 to confirm that our instruments are valid and the exclusion restriction holds. To wrap up our look at instrumental variables, let's use this three little pigs analogy for the diagnostic suite. First, we have the brick house, representing relevance. This is your foundation. The link between your instrument Z and the endogenous variable X must be strong. We verify this using the estat first stage command, aiming for an F statistic greater than 10. Second, we face the wolf, an external threat representing exogeneity. Our instruments must be truly exogenous, remaining outside the error term. We test this with estat override, where a p-value greater than 0.05 suggests the instruments are valid. Finally, there's the comparison, which addresses endogeneity. We use estat endogenous to determine if IV is actually necessary. By rejecting the null hypothesis, we confirm that OLS is biased and the IV approach is the right choice. In short, a robust IV model requires a strong foundation, safety from external bias, and a clear reason for its use. To conclude, we provide a list of essential resources for further study. On the academic side, Cameron and Trivedi offer a practical guide to Stata implementation, while Wooldridge provides the deep theoretical rigor needed for complex panel data models. For understanding the critical nuances of weak instruments, Stock and Yogo's 2005 paper remains the gold standard. For hands-on help in Stata, the built-in documentation for ivregress and its post-estimation suite is incredibly detailed. We also recommend the user-written command ivregress2 by Baum, Schaefer, and Stillman, which is widely used in research for its more comprehensive set of diagnostic tests. Thank you for joining us, and we hope these resources help you master instrumental variables in your research.